Feel proud today. Courageous. Okay, so ductile or brittle. For those that said ductile, help me. Understand. I'm your manager. I don't know very much, but I need help. I know that. Why is it ductile? Why is this a ductile failure? Necking. So we see a reduction in diameter of the cross section in the gauge section with respect to that of the non-tested specimen. So I see the macro characteristic is reduced cross section. And actually, what I would say occurs to this material is it's probably best described by a profuse necking type of distribution. So what happens to this material if you conduct it at the right strain rate, relatively low strain rates, and then you also not use if you don't use any gauge clips to be able to apply an extensometer to monitor strain that creates stress concentrations by contact, it'll elongate initially in one spot, and the necking point will continue to profuse, or it'll continue to extend along the entire length of the specimen until it gets to some particular state. Okay, what else can I see? I have one then piece of evidence. It suggests that this is a ductile type failure or involved inelastic deformation. What else do we look at? Mesoscale. What's the fracture surface orientation tell me? And when I pass it out with a loop, I'll pass it out again with a loop. So now you don't need this one, you just need the failed specimen. But I pass out a loop so that you can look at the fracture surface. Okay? You should be able to see something very characteristic. See. I doubt, I'm your manager, I doubt that this is a ductile failure because I see that the fracture surface is at 90 degrees to the orientation of the maximum load. What does that tell me? Suggests that this is a fracture surface orientation. Says brittle. And I'll say it is not cup cone. Micro features, if I look at the surface, I can actually see radial lines that extend from near the origin point. So it has some kind of stuff here because actually this was in a universal testing frame. It was subjected to increasing magnitudes of tensile load until the fact that it fractured. When it fractured, the grips actually released their elastic energy and enabled the surfaces of the specimen to actually contact. And so you'll see that in one of the portions of the corner. It does that, but then you'll see this. So those are radial lines that we're used to seeing in bolt fracture on what kind of surfaces? Brittle. Those are brittle characteristics, okay? So we see radial lines. So this doesn't make sense. I see ductile or non-brittle, and then I see kind of brittle, and then I see another thing that looks like brittle. Why could that be? This is a ductile brittle. How many of you took the polymers class? See, 1, 2. All right. Help me understand then what happens in this material when it deforms. Does it deform along slip planes?
It's the polymer chains until they're stretched out and they.
Okay. And they align themselves to the direction of. Well, they align with respect to the stress, but they're guided by the backbone, I guess. And so they're aligning themselves with the direction of maximum tension. But are there slip planes in that polymer?
No.
No, there's no slip planes. And so you know that for a cup cone fracture to exist, it exists in metals a lot because those metals generally will have slip planes that are defined to be consistent orientations along the unit cell to enable then slip along those adjacent planes of atoms. If you don't have a slip plane, which this polymer does not, it can't allow this cup cone fracture, the shear lips are a result of that slip process. So This can undergo inelastic deformation, which is evidence of necking, until the fact that you absorb all the inelastic capacity, which is just the realignment of those polymer chains, until they all become axial aligned. And so we end up with something that in that tensile specimen might have started like this. It was slightly influenced by the extrusion, but then by tension, they all begin to align and then reduced in diameter. And then there are no slip planes. This still has orientation of maximum shear stress at a 45-degree orientation, but nothing that enables that to result in a shear lift. So this started as a ductile process. It continued through a inelastic deformation, but it ends in a brittle failure characteristic because that material cannot fail by development of new surface area through a ductile mechanism. Okay? So, we don't talk about polymers a lot, but you can apply the exact same things in the way of thinking about how the microstructure influences the responses. Okay? So, by definition, that's a ductile failure. But at the end, you will remain or only see the brittle characteristics on the fracture surface because all the ductility was exhausted in that process up to the point in which you developed your surface area. Okay? So that's like your 170 stuff, and then I think, what course is this? Polymers course? 471, maybe you got a little bit, but then also 362, you might have talked about polymers a little bit as well. Any questions? Okay. So we were talking about fracture surface markings in materials that occur by fatigue crack growth, and we said that, the initiation stage, if we have a crack that starts from the surface, and it doesn't start from a well-defined crack that might be a result of service or manufacturing, it'll start as a result of this process in metals again, which is shear initiating slip along appropriate slip planes within near surface crystals. And then what will happen is once those slip bands enable a well-defined crack to start, the crack will be taken over by the magnitude of the opening mode load. It'll turn itself to take advantage of all that energy, and then it'll start to grow in a conventional opening mode fashion. And I said, you might not see that in the edge of your specimens because most likely those cracks started some other way. They didn't start by intense deformation on the surface. They started due to other defects that were present. That would be the majority of the case. But nonetheless, then what you'll see is once those cracks start taking off, on that portion of the surface that's right here, you should see the history of that slightly cracked extension. So you'll see striations that will be present on the surface, and they should continue all the way up to the point you reach the point of unstable fracture, and bulk fracture comes through the specimen as a result of linear elastic fracture stuff. Okay. So there's a mechanism that's responsible, and so I picked up a schematic that I saw that was a portion of a print that was in the ASTM handbooks, not your ASN handbook, but it's a schematic which kind of describes what goes on mechanistically and why you see these features on the surface. So let's say, for example, we've got a crack in a specific specimen. A lot of times, when we think about cracks, we think about them looking like this. Right? They're infinitesimally sharp. Very, very sharp. There's no radius of curvature at the crack tip. So if I blow this up, and if I show this at magnified view, it still looks like that, right? Whoops. Here. Still looks very, very sharp. But in reality, if that material has any ductility, then what's going to happen is we'll see a pattern that's quite different. So envision that this is a crack starting from left, growing to the right, and then what goes on is it's reached a point where we're going to examine it. So when this is close to stress-free, or it's subjected to a small amount of compression in the cycle, the surfaces of the faces of the crack are closed. But then when you apply a little bit of opening mode load, what happens is that because of the intensification of the stress at the crack tip, the huge increase in the magnitude, then there will be potential for plastic deformation to occur near that crack tip. And that will occur preferentially along the planes of maximum shear stress. And so that will occur on these 45-degree shelf angles that are simply defined by Morse circle, right? So that will allow actually new surface area to generate specifically on those diagonals, those 45-degree orientations with respect to the plane of the crack. And eventually what will happen is the crack will open up wide enough that it starts to enable new surface area development just by the continued plastic deformation process. The crack ovalizes, and the amount of ovalization is going to be a function of the amount of ductility. So then what happens is that deformation from here to here caused an increase in the surface area of the interior of that crack. So now it's like this, it's like a sweatshirt that got stretched out because I had a big belly. And then when I lose it, my sweatshirt didn't change, and so it just hangs there as an extra amount of material. And the same thing happens to this crack near that surface. As the crack begins to close, that means as the loading undergoes the reversal, you'll see that that marking of that intense increase in surface area is left on that surface. So when the crack actually becomes zero stress, you get that little nub in there that's just really a result of that small amount of the elongation that occurred around the surface of the crack. And the process then continues to the end. So each time you get a cycle that's large enough to introduce plastic deformation near crack tip, you get that signature of the crack saying, I moved a little bit, but I was subjected to enough deformation that I actually extended my surface area. So that says if that's the mechanism, then ductility is a big requirement for seeing striations. And indeed, that's the case that we see. So we know that striations are something that's quite different than beach marks. Beach marks are a result of sort of, the changes in the environment and the rubbing features that occur on cracks. Striations are going to be very, very small, and they're visible only with an electron microscope. So you have to remember that. You'll only see them in highly magnified views. And then we know the mechanism now, because I discussed that, it's really dependent on the ductility of the material, whereas beach marks are, as I said, they're quite different. And you might see beach marks not being so periodic, because they can be a function of different cyclic environments. So I had my marine, my boat in a particular warm environment, and then I went to a cold environment, and the activity of the corrosion process, the oxidation process in the crack changed in cold and warm. So I would maybe see that on the crack surfaces in that cycle. And then the striations are most evident if that crack was subjected to really opening mode load, and this material has large ductility, and that material exhibits very low degrees of world hardening. That means we get the most plastic deformation near the crack tip. So here's some pictures. Two different things I found on the internet that are actually striations, but they show something that, I had a question. Should we see a striation? If I conduct 200,000 cycles, we'll see 200,000 striations. We could if the material has the capacity to show that. So when the crack is just starting to undergo cyclic deformation or cyclic extension, our distance between the adjacent striations becomes very, very small, and then also, depending on the ductility and the amount of the rubbing in the fatigue cycle, they get potentially washed out. So here's the start area, and you'll see the fatigue striations only extend and get really well defined as we go further and further from the origin point on this particular component. And then what you'll see here on the right is actually a mixture on this chromium fracture surface of a hip implant. It's examined by SEM, but there's a beach mark that's right there, and there's probably another beach mark, but the rest of this stuff is actually striations. And I apologize, there's a big problem with these. The problem is you don't have the DAR markers to show you what the scale is to indicate, hey, I know that's really a striation. Because that looks like a bunch of beach marks at that level of magnification. But you also see something there that's pretty important to you. Those are ratchet marks that are extending from the origin point. So those are the beach mark locations, and then these other things are the striation position. The fact that this is not periodic means well spaced, that they're all the same spacing, means that this is really quite different in the magnitude of the load that caused each cycle. So you might think, hey, this could have been a pole vaulter. They had some big cycles, right? And then they had some cycles that were really, some other stuff. That's what fatigue can give you in terms of the information. So here is a great example of different characteristics of striations. This is actually from a Hertzberg's textbook. These are both electron micrographs by transmission in electron microscopy and also scanning electron microscopy. So A, you'll see it says TEM of a constant load range. And so you'll see the striation space in here is actually very constant along the whole length of that process. Now, recognize that striations, they bow because of what we talked about in terms of the interior of thick bodies are subjected to, most likely, a plane strain condition, more brittle. So actually the crack advances faster in that region than it does around the periphery because it's under plane stress. So anytime I see marks that have sort of a curvature, I know where the crack came from. That's one thing. So I would say, hey, the crack came from up there, and it went along that direction. B, it says SCM of a constant load range. Again, another example here, constant load range, but much different features, okay? So SCM versus TEM. So in this case, in C, it says TEM for random loading, and in D, we see that in the striations. Spacing is wide, and then it goes narrow and non-defined, wide again and narrow. So there's a fatigue cycle that was probably changing in amplitude. It probably went something like just like that. And you can see those traces then on that particular specimen because they'll show you how long the crack wanted to go. We see TEMs of ductile striations, very deep and dark striations, differences that are caused by TEM. And then something with not quite as much ductility at all, brittle striations, so you can just barely make them out. Brittle, meaning that we don't have enough ductility to leave the signature of the crack. Okay? Do we have anything else here? So spacing, we know that spacing is a function of delta K, and delta K is a function of delta S, the stress range. So anytime that I think that the stress range increases, I should see the spacing increase in dimension as well, right? And then we might see that the inconsistency in load cycling tells us something about how that crack grew. So, you know, you could have someone tell you that we believe the cause of fracture was the fact that this was overloaded, this structure, and then it was subjected to normal loading, and then that one observer, or that one operator in this shift always overloaded. You should be able to tell if that was really the case by looking at crack striations if you know that fatigue crack growth was a part of that fracture. You could trace back to see if you knew that inconsistency told you that there were actually differences in shifts by the way that things were operating. Wow, that's really cool. Amazing, right? And can you imagine going to a courtroom and showing a group of people that you could tell when a component failed, but you could also tell what kind of loading it was subjected to over that history of the process. That should be a, you can do that by science. Fantastic stuff. So, there's some good examples in your handbook. Figure 33 shows some examples of striations in 18.8, often in stainless steel, under rotating bending. It shows you in A some very fine striations that were in this particular material. It says midway between origin and final overload fracture, okay? So in this case now, the delta K was smaller. So how do I know that? I want to make sure that you see this because this is an important part of you connecting the science to the observation. So this is a okay, so I'm thinking about this magnitude is a function of this that's taking place as the growth, the driving force in our crack extension process. Delta K can change with extension, and delta K is changing because as this increases, the delta K value increases as well, right? It increases from the point where the crack started to the point where it went unstable. You're waiting for this to take place, that your K max, which is your Fs max, square root of pi A sub C is equal to K1C. So we wait until the crack grows long enough that it actually results in bolt fracture. But in all this time, the crack is gaining driving force, and so it should be extending a longer and longer distance in each cycle. And you can actually see that. So these are striations of that same material, but closer to the overload area. So we know that the magnitude of the stress intensity, the driving force, was greater and causing bigger striations, more pronounced for the same material. So here we see, for example, coarse, very coarse striations, and then fine striations that you see on a hot isostatically pressed titanium alloy. And, you know, in both of these, you can kind of tell what's going on in terms of the orientation. So here, for example, I see that there's striations that are increasing in amplitude. What direction is the crack growing? From top to bottom. I look at these striations that are present here, and I'm looking for features that help me understand. What do I see? They're very fine, maybe really almost impossible to see from your vantage point. Let's see if I do it all off. What can you see? So if I had nothing else to look at, I would say this crack went from right upper corner to bottom left corner. But I want to get more information. Just from looking at the fracture surface, you should be able to have at least some feeling about what's going on here. Okay. And then we have the ones here on the right, which are actually striations that are present in something that has much less ductility, it's a medium carbon steel. And you can see, for example, that now what's going on is that deformation is already extended past the ductility of the material. It's called microcracking around that crack tip. That's a lot of good stuff.
When you see rotational bending in this context, is that taking a shaft and torquing it?
That's a situation where you have a shaft and it's subjected to a bending load. The bending load doesn't change orientation, but the shaft is rotating. So all of the surface is subjected to the same magnitude of maximum tension and maximum compression. Because on one cycle it goes from, because of the bending moment, maximum tension to maximum compression.
Okay.
So that's exactly what this is. And that's important to know because that means that the crack faces are actually touching when they go through the compressing portion of the cycle. And they can start to walk or not walk, but they can make the striations become less pronounced because they actually got contact, physical contact.
We were talking about this last night. If I have a shaft that's being fatigue loaded in twisting, basically, is my crack going to grow in towards the center, or is it going to grow sort of circumferentially?
Depends on what drives it. It'll drive, so let's say, for example, that you had a shaft, this was the problem, and then what happens is subjected to torsion, it looks like that, right? Mm-hmm. And I get a crack that, let's say, that starts like this. It was some damage that was introduced as a function of something. Is that your situation? Yeah. So, you look at the stress element. The stress element says that it's subjected to this, right? And it says that that's the plane of maximum, that's the direction of maximum tension. So if I'm looking at a stress element with rotation of 90 degrees, there's the direction of the maximum tensile stress. So my crack would start to grow, and then what would happen is it would want to do that. And then it would start to grow that way as a penny-shaped crack, which would orient itself because that's the direction that the maximum tension would be working on that particular shaft. Right? So it would start, and then you'd see it turn, and then it would go to the point it became unstable. We actually saw that in one of those cases in the last lecture that was that drive input shaft for that NASCAR. That exact same problem. Yes.
So when you point at the striations, you kind of say that it starts from the top to the bottom. I get that when you have the bigger fracture surface, it's like pretty clear to see where it started, but like when it's focused in so much, can you actually tell like top to bottom or like top right to bottom left, or is that what's
So, good question, and it's kind of dependent on the amount of window evaluation that you have available to you. Because if you only see striations that look all straight, you don't have much to go on. You look for the spacing that can help you. You look for rising delta K, but might not be helpful either. The best sign is when you see striations and a bolt fracture surface start. So that's like, okay, that's a no-brainer. But you might not always see that, and you might be asked to comment on things when you can't control who's operating the SCM and they give you these figures. You say, okay, well, I have to try to figure out what I can with the best of my background that I have. Other questions? Okay, so what can you do when you have striations? Let's say, for example, we have a case where we're asked to be able to look at something that's taking place in a material, and we have a good example of a fracture surface with striations. So here's one. This is this case, figure 33, and this is this 18A austenitic stainless steel, and I have the striations that are very well defined. I know the direction in which the crack was growing, and what I have is an area where the striations look about they're all common spacing. What I can do is, hopefully, I can say that I know that this is an area where Paris law applies. So I know that this is the case, and I can say that that should be defined by Paris's law, which is A delta K raised to the power n. When I see the striation markings, I can get the delta A delta n. So it looks like that crack went 15 micrometers divided by my 5.75 striations. A striation in this material is a result of a cycle. So that's actually 5.75 cycles, right? And, you know, I forgot my notes. And so if I remember correctly, that's about 2.6 something times 10 to the 9 meters per cycle. You might want to check that, all right? Because like I said, I'm trying to remember what that number was that I had. So there's gives me the dA/dN, right? And what I can do with this is I can say, hey, if I know that material well, that means if I know that 18.8 was not subjected to something that scares me, I can start to say that my delta A over delta N divided by my value A raised to the power 1 over N is equal to my value of delta K. I can back out what the stress intensity range was on that particular specimen, right? I know what the driving force was that worked on that material. And the way that I do that is I go here. So I look for the material and I hopefully find it. So that says austenitic stainless steel. There's my slope, N. There's my value of A in meters per cycle. And then I can use that to be able to predict, you know, what I would get for that value of delta K. So I don't have enough time to go through this here because of course I want to move on. But I'm going to send you an example of using exactly that for this problem and go through the rest of it and give you the information about calculating and estimating the maximum cyclic stress in this particular material from this data that we just developed here at the dA/dN. But the most important part is using the striations for something that's valuable, okay? And that's it. Getting an estimate of how fast that crack is going every cycle. Now remember, this is not a speed. This doesn't tell you how fast the crack grows as a function of time. It's as a function of cycle. So you cannot make that mistake and think that that's a velocity of a crack. That just means every action of that driving force is what causes that crack to grow. And then what I do is I end up showing you in that example that we develop actually an estimate for delta K that's about 55 megapascal square meters. And I look and I say, hey, where does that actually end up? You know, in terms of the austenitic stainless steel responses, it's right here. It's at the end of the stable portions of cyclic crack growth. So there's my value of 2.7, like I said, or 2.69 megapascal square meters. It actually agrees very well with what Barsum's estimated dA/dN value would be. But the other thing is if I go back to that figure, and rather than read this way, I'm going to read this way. It says here, B, core striations were located closer to the overload area. That means closer to where the material was undergoing or going to undergo bulk fracture. And so when I see it, I go back here and I predict what's going on. When I look at that response, I estimate a 55 megapascal square meters. There's almost no data there. What does that tell you? The data doesn't exist because that crack's no longer growing cyclically. It went unstable. This is just too exciting. This is like, wow, I get paid for this stuff. That's a okay. So please look at the example and look very carefully because you can't miss the value that comes from looking at this stuff and using it for the purposes that you have available to you. I loaded notes for the remainder of the next 3 days, and the first thing that we're going to talk about is we're going to talk about casting processes. Because now we know the defects result in failures, but we want to make sure that we understand where the major defects are from certain kinds of manufacturing processes. Where do we look? Because we looked at things that help us understand why failure took place, but not the origins, potentially not the root cause. And so we want to make sure we see root causes. And these can be contributors. We're looking for the hidden roots, the ones, the physical roots that are associated with the material defects and or the manufacturing and processing, maybe the installation, but that could be really what causes stresses that are different than what you expect. Okay? So we're going to look at casting processes. These are the major manufacturing processes and sources of defects. Today we'll talk about casting, we'll talk about metalworking next time, forging, etc. Then we'll talk about machining and heat treatment. Then we'll talk about welding. The rest of the stuff we'll have to talk about. So this is the majority from section 8, and you look at, what section 8 has. This failure is related to casting from 103 to 152. Wow. Casting is a big source of failure. That's what that should tell you from all those pages. We won't cover all of that. We're going to try to do something that makes this as quick as possible, but as valuable as possible. So casting can be divided into two different regimes, either expendable mold or permanent mold. The expendable mold process means that a mold is made every part, and then what happens is you shake out your part, and then you make a new mold for the next particular part. The most common expendable mold process is sand casting. The advantage is you make very complicated shapes with respect to the other regime, but the disadvantage is, of course, the production rate is relatively low with regards to the permanent mold processing, because this takes a lot of usually hand labor, hand involvement. Also, the disadvantage as well is the fact that you use sand for the molding material. Sand is not metal. Sand is, when you go home from the beach, what do you find? In your shoes, in your pants, in your shorts? Sand. So sand carries everywhere, and it does the same thing in terms of your metal parts, if that's what you're doing. So you have to worry about those pieces serving as defects. But it's a permanent mold process, then the mold is made of metal, a higher melting point metal, or a non-metallic material. For example, a ceramic mold can be used. The advantage is very high production rates, but the problem is that the geometry of, or the detail, the level of detail is lost, because you have to be able to remove your part without damaging the part itself. So in expendable mold processes, we have to be able to use a binder for the sand, make the mold, densify the mold characteristics, pour the metal, and then shake out the part. And all of these processes contribute to go like this, and then this, and then this, can actually contribute to the introduction of defects that might be present. We'll talk about the major features that you can get. You cast, I think, in this department, right? A little bit. And this is in 312. Okay, great. What do you cast? Aluminum. Great. Okay. So you have a little bit of experience, and then what you should be familiar with now is that, in expendable mold processes, we either use an open mold process, or we'll use a closed mold process that involves really using two flasks to be able to define the shape of the part that you want to achieve, divided between the cope and the drag. And then what there is there's some binding clips that are used to be able to hold those two pieces together. And we invest then in that mold material, the sand, the shapes of specific features that we need to try to obtain a part of the right kind of geometry. So in this particular cross-section, we're going to pour the metal in the mold, and then this cross-section shows the runner and the gate systems that's used to deliver the metal to the actual part cavity. So there's the cast metal cavity, there's the core, of course, that might be used to introduce internal features. And we always think about the parting line that's present in these particular components, because the parting line references the line of, not necessarily symmetry, but the line of division between the cope and the drag of that mold that's used to be able to develop the part. Okay? I'll bring parts with me next time so that we'll talk about that and the importance of that in failure analysis shortly. Okay. But so when we think about a hot chamber, or excuse me, a die casting process, then what we're doing is we're melting the metal in the furnace, and then what we're doing is we're introducing that metal in a quite different mechanism than we're doing here. So in this case, of course, the metal is introduced in the mold, and the only pressure that's developed to deliver that metal is the potential energy, the difference between the distance of pour to the actual line in which that metal runs along the gating system and enters that particular part. So if there's not enough potential energy there, then there won't be enough pressure to actually force the metal in the mold. And that can cause problems with the metal not completely filling the mold cavity, getting what's called an incomplete runner or a misrun. That's one of the advantages of using, for example, a permanent mold process or a die casting process. In this case, we're melting the metal in the furnace, but we're going to pressurize the metal at much, much greater pressures to be able to get complete filling capacity, right? And that results in higher production rates because of the automation, but it also results, in some extent, a slight difference in the kind of metals that we can develop parts from. So if I go back to this process, we can almost cast any metal because the melting temperature of this material, non-metal, is much, much greater than that of any metal. So the metals we're looking at might have melting temperatures on the range of about up to 3,000 degrees Fahrenheit, maximum. You know, and the steel is just going to be like around 2,600 or so, and that's no problem to be able to cast within a sand assembly. That won't happen here. So if we look at the expendable mold processes where your mold is typically metal, then we're going to use, for example, in hot chamber, a zinc, a tin, a lead, a lower melting temperature material versus cold chamber, which is a little bit higher melting temperatures. We'll add aluminum and brass, and then some of the more exotic magnesium alloys that have higher melting temperatures. Just this is background. I think you get this in other courses. So in a hot chamber process, what we're doing is using a furnace to hold the volume of metal, and then using slight amount of pressurization to move the metal in the mold, get the part, and the runner stays hot. So actually, if we just reverse the direction of the pressure, so this is a feed direction, we fill the mold, we then reverse the velocity, and then what happens is we open up the pressure, and the remainder of that liquid metal just comes out of the gating assembly and is removed. And then we just, at that same time, we remove the part from that mold assembly, eject it from the mold assembly, and get ready for the next injection. This is important from a defects analysis because of the following. These are metal, and metal has a certain thermal conductivity that's different from that of this material. And what is that relationship? Of course, in this case, the sand, this is a sand that's mixed with a small amount of clay and a small amount of water also to hold that assembly together. It has much, much lower thermal conductivity. So it can't remove heat very fast. That influences grain growth. It influences grain orientations. And that makes it these two processes can have much different microstructure that's really important to the way that you might see those components can fail. So in a cold chamber die casting process, that means that the metal is brought to the mold in an area remote from actually the furnace. And that means that the metal is much cooler at introduction to the mold and is done as a single control volume shot process. It's done under much higher pressure because the metal has much lower viscosity. Much higher viscosity. It is much less like a liquid. It has a resistance to the flow of its introduction into that particular mold. But that also is, again, important in just comparing the cold chamber to the hot chamber. This material will likely have more time for changes in grain growth. We're going to talk about it next. Okay? So, temperatures, important to whether this is expendable or non-expendable. And then also, to some extent, surface finishes, because in this case, your metal is contacting a metal mold that has very well-defined surface roughness, high quality, low roughness, whereas in the other case, our metal is touching, of course, sand. And you made sand casting so you know what that surface is looking like. For all of those processes, the most important part to begin with is going to be the temperature at which that metal enters the mold. And the reason that's important is because it controls what's called the superheat. So anything that involves a failure analysis and a casting would have to be involving also what's the level of superheat that's used for that part. The superheat is the pour temperature minus the melting temperature. That tells you the amount of the increase of the temperature that's present. This is a function of time, but it's always tried to be minimized in all casting processes, regardless of what the focus is. And the reason is twofold. So we could be pouring, for example, a pure metal, so a pure aluminum, or for example, a pure copper, versus an alloy. So for a pure metal, if we don't have any alloys to be worried about, or we pour an alloy with a eutectic composition. Eutectic meaning it goes directly from one phase to another phase with no intermediate exchanges. Then what's going to happen is we pour, we have a specific superheat, and the superheat is the distance between the pouring temperature and the melting temperature. We see that from the pouring temperature, that material, the liquid metal, has to undergo cooling through heat transfer with the mold until it gets to the freezing temperature of that metal. And then what happens is the metal will stay at that constant temperature while freezing progresses throughout that volume, which controls the solidification time, and then the latent heat of solidification is removed, and then further conduction occurs with the mold wall. So this is really the total time that your metal sits in the mold. So we reduce superheat to be able to make sure that we reduce that as much as possible, and that this time frame is as small as possible per part. But also we do that because all of this stuff is heat that's conducted in the mold wall that brings the mold wall temperature up and then keeps the remainder of the conduction process at a slower rate. So you can end up having less heat conducted from your metal because the mold was heated up during that process and now can't conduct that heat as efficiently. Okay? So we'll see now that what we'll find is, let's look at a bond metal that was introduced within a cavity that was liquid, and it's in contact with the mold wall, which is in orange. So all of this metal was liquid, and it was shock solidified because it went from the room temperature to the melting temperature of the material, and we get very, very small grains that are epitaxial. You know, they're very, very small, consistent grains, and then what will happen is then the remainder of the solidification process will follow the heat source. The hottest metal is always in the center, so the grains are following that process as they continue to grow. And we'll get these columnar grains that will extend from these epitaxial grains along the boundary. Which part of this casting is stronger? If you were to choose any portions of that area that you can see as a cross section, which is strongest?
The outside.
The outside, that's correct. Why?
Smaller grains.
What tells us that those smaller grains, that's exactly right too. What tells us that that would be the case? Let's say sigma naught plus K over the square root of D. What's that look like? Yeah, this is definitely something that you have used and you know it applies here. This is the Hall-Bench relation. So a casting will always have its strongest portion on the skin, and the interior will be the weakest because the grains are larger, because heat conduction was less rapid. And then also right at this point you have an intersection of grains. So you also know that these in this case will likely be areas of triple junctions, and those triple junctions will have more intermediate points or more locations, which is potentially an interface that can be weak.
Is that sigma equals sigma naught plus B over square root of D?
K square root of B. So this is a base yield strength, right? So if we're looking at yield, let's say we're looking at strength, and then we have some D, and then we have some particular base yield strength that would be present. You know, for a reference, when D is 1 grain, right? It's a base yield strength. And then what we have is an inverse relationship with square root of D, and K is just what's called a strengthening constant, right? It's just a constant that's used as a curve fit in an experimental evaluation. So base yield strength plus an addition that increases the function of the decrease in grain size. Okay, so when we look at this response, we know this is the weakest and this is the strongest. So how do we make a casting as strong as possible? We make all this go to the entire thickness. That means we use thin parts, so we try to control this solidification process. Or what we do is we minimize the amount of heating up of this, and we try to extend that area as far as the interior as we can. So when you change the casting conditions, that might be part geometry, or might be the temperatures that are associated with pouring, that will influence then how fast it's taken away, and that will influence grain structure. That's U, right? So that's how the processing will be connected to the microstructure, which will be connected to the properties. You want to make sure that you look at that. So you look at this, and then you look at grain structure sizes, the distribution, and you look at exemplars to see if this has changed as a function of the process. Now let's consider a non-eutectic composition of an alloy. So in this case, we have, for example, a good example would be a Manel, which would be about 50% nickel and copper. And so here's, of course, the freezing ranges that you see for 100% nickel and 100% copper. And then we should use the level rule to be able to find the freezing range that occurs from a pouring temperature all the way to the material coming back down to room temperature. What you see now is, again, a superheat which defines the level of extra temperature from pouring temperature to freezing, but then there's going to be a range in the freezing in which we find that the liquidus undergoes the first point of freezing, and then we follow with the solidus range, the lowest freezing temperature metal, and then that latent heat of solidification is further removed by conduction. Okay? So the total solidification time, again, is this total time from pour to the point where the metal is completely solidified. This is important because, again, the part's going to be shaken out of the mold at that particular time. You can't shake it out earlier than that. You won't wait for the metal to come to here, you'll go here. This part looks like it's the same range for pure metals and non-metals, but it's not typically, because in this case, this metal is going under many different things. So what can happen is we'll get segregated solidification. We'll start to get, of course, the liquidus component that undergoes solidification first. This will be probably uniform solidification. That means of the alloy as defined. Then what's going to go on is, after that shock solidification, we start to get material that understands that, hey, it can have time to solidify preferentially, in which now the material which has the lowest melting temperature will be pushed to the interior of the mold. So your materials now can end up being segregated in chemistry and also segregated in terms of the grain structure. And that's a big deal, because you would like the entire part to, of course, be looking just like that. And you chose an alloy for specific properties, right? And you might not get that at the center. The greater the thickness of the part, the less likely you are to get that uniformity. When this solidification takes place, you know that it's most likely going to take place by dendritic growth. So the dendrites are forming from the skin solidification on the periphery from that point. And those dendrites then have less fluidity. That means that they're causing obstacles in the flow of the liquid metal inside that part. So there'll be obstacles to the actual distribution and fully filling of the mold. So there's a lot of things that you have to be worried about if this is a non-integral alloy. Okay? But mostly is grain size. The next thing that's going to occur is, if you're able to fully fill the mold, and you know that, for example, that you might have some movement of the metal, as well as there any shrinkage that took place. So we're going to find that all of these materials, except for probably one, is going to undergo shrinkage as a function of solidification, and that's because, of course, the higher density and packing factor of the solid versus the liquid. You'll have a reduction in the volume per unit weight, of course, of the metal, and the exception to that is just cast iron, which, if they have high enough carbon content, they'll get graphitization, which develops, in which it will actually expand during the solidification, not contract. And then that becomes important to being able to use a mold that doesn't constrain that expansion, because it will cause cracking if it has enough internal stress at the hot temperatures in which it's undergoing this solidification process, right? So what can that cause? So the liquid metal, which we were worried about before, can enable segregation. That will also be locations that we can expect to see voids. And the reason is because the outsides of the mold will always be skinned, and the metal will fall to the center, and if this skins develop that restrict the ability for metal to fill the mold, it'll actually shut off the flow of metal and you get these from the voids. So next time that we meet, I'll bring examples of parts of that